Now we have Sina Hazratpour talking to us about towards the group-wide model of fighting Lean4. Slightly different from the previous title, but that sounds good. Thank you.
Okay, thanks, and thanks for coming. This is my last day at Hausdorff, so it's nice to give a talk as well. So this is a work we have started with Steve Audi and Mario Carneiro, and later some people from CMU joined us. We had started this work actually at Hausdorff Institute in June, and this is a work in progress very much. So yeah, this stuff are under development, but I thought maybe it's a small audience, so I give a sneak preview of the work, and if somebody gets interested to join us, that would be great. So this talk is about bringing two different type theories together. Homotopy type theory, there has been several talks here, so I'm not going into giving another introduction to homotopy type theory, so most people are either familiar or you have at least heard one of those talks. And there has been many talks about Lean, so this work is about sort of combining the two to get benefits of homotopical reasonings, maybe synthetic homotopical reasonings in Lean. So let me give a little short history of, I mean, this idea is not new, it's been tried. I mean, we are not the first to observe that it would be nice to have a synthetic reasoning in Lean. So it goes back to Lean4. So this is work by Floris and many other people so this is the first link essentially. So in Lean4, you had a special support for homotopy type theory. So you had the standard library of Lean, but there you had the option, a flag option that you could set it like hot or Lean. Of course, these two were inconsistent, so you could not have both at the same time, but you could switch between Lean and hot, and it's nice that same syntax of Lean, like you don't need to learn another programming language or syntax to do both different type theories. So that's definitely nice, and some serious homotopy theory was done in this system. So Floris did spectral sequences in Lean4, but you can see lots of other constructions in homotopy type theory. I don't know how much of book HoTT is there, but a good chunk, I guess.
Yeah, most of it, almost everything in the later.
Right. Nice.
And they also shared code, right? There was some common code between the standard library and...
No, because they had incompatible kernels, and they have incompatible equalities. There was very little code.
So I asked Floris, so I don't have Lean4 on my computer. For preparing this talk, last night I was trying to install Lean4 and try this, but I failed at that. This doesn't say it's, I mean, I don't think it's hard. I had to split my time between preparing the slides and actually installing that, so my patience was limited. But maybe today I try that. So going to Lean3, this support was gone in the kernel. So the kernel did not support homotopy type theory anymore. And of course, so people started writing a tool which basically tracked. So you could still write hot stuff, but then of course you should not use some of the stuff that makes it inconsistent with Lean type theory. And people wrote a tool essentially to track uses of anti-hot stuff. So if you write an anti-hot thing, then Lean will give you a message using those stuff, so it's an error message.
Do you know by any chance have any idea why this flag was removed? I mean, it was literally just an option.
These are early days of Lean. I actually joined only Lean4, so maybe experts.
So Lean3 was completely right from Lean2, and we always think overwhelmed. So just didn't have that. Didn't have
I see.
Okay. So this is sort of like a cartoon of our effort. It's different than both of those previous efforts. First of all, we are way less ambitious. I tell you why. And second of all, the approach is different. So the approach that we are taking is like we want to have an embedded type theory inside Lean as a sort of like DSL, where you have homotopy type theory, essentially. Then we want to get the terms of that type theory and compile it to something called natural model, which I'm going to explain here. And then this natural model is a sort of like algebraic gadget where the rules of type theory are encoded in it. And then this algebraic gadget, you can then interpret it to models that you think are going to model homotopy type theory. So the groupoid model of Hoffman and Schreiker from 1995, it's not a full model. I mean, we know the problems. That's why Vladimir Vobotsky came up with a simplicial model. But nonetheless, it's a good test model, you know, as a sort of test case. And the good thing is, like, we have groupoids in MATLAB. So we can write this. So we can write that DSL and we can compile it down to the model. And not only we have a type theory, but also a model in Lean. So everything here is in Lean. And once infinity groupoids or complexes, we have simplicial sets in Lean, but
The definition of complexes.
it's there, right? Okay. Right. But once infinity groupoids become available as a theory, maybe we do some bigger effort to get interpretation of natural model and therefore this DSL into that.
But why do you say the groupoid model is a simplified model?
Well, groupoid model doesn't have higher homotopies. I mean, so homotopy type theory gives access to all H levels from 0 to infinity. It only has like one-dimensional path rather than path between paths.
Okay, cool.
So to explain what natural models are, I have to give a prelude to polynomial functors. Hopefully it will not be too long. Then I spend some time on natural models, and then I explain how the natural model can be interpreted in the groupoid model. Depending on how much time I have, I might, and if people are interested, I can show some of this embedded type theory as well. Yeah, okay. And in between the slides, there will be some Lean code, so from formalization. So what are polynomial functors? So take a category C with finite limits, so you have terminal, object, and fullbacks, that's all we need. Take a morphism P from E to B in that category, and assume that it's exponential. So exponential basically means you have a triple adjunctions here. So this is C over E, slice over E, and this is C over B. And yeah, so you have a bunch of adjunctions. I tell you what those functors are quickly, but just a very syntactic observation, when you take B to be the terminal object of the category, then you go from the slice over E to a slice over 1. But the slice over 1 is just C. So therefore you go from C over E to C, and I just, instead of, then you don't have really P, because the map P now goes from E to the terminal object, and there's only one of them, because terminal object has the universal property. So the data of P goes away, and essentially all you have is the object E. So I'm going to use this notation. So I'm overloading notation here. And actually we can do this in Lean as well. You can write an elaborator that overloads notation. Because all of these things take morphisms while these operators are taking objects. So here are definitions of those things. So sigma is essentially, so if you have a morphism over E, you compose it with P, and then you end up on the slice over B. So it's in Lean, it's called over.forget. Delta, it's given by base change or pullback along P, so that's over.pullback. And pi comes from the fact that pi is exponentiable and becomes accessible as the right adjoint to delta. So given all of this, given P and these functors, we can compose them to get an endofunctor from C to itself. And this is the so-called polynomial endofunctor associated to P. And in the internal language of C, so if your category C is types, for example, this is honestly equal to this. And otherwise, you can use the internal language to express, like, this is up to internal language interpretation. So you get the old familiar polynomial expressions. So EB here is the fiber of E at B. Okay. So this is how we wrote it in Lean. This is a formalization of polynomial functors that Emily and Mario and I don't know, maybe myself and some other people did also at Hausdorff Institute. So I put a link to this at the end of references to this formalization project. So now let me Good. Any questions so far about polynomial contours? Okay. Then I'm going to use them to define this gadget of natural model. Yeah, so let me just show you a link code and maybe I can elaborate on this on the blackboard. So this is how we define natural model. So what is a natural model? Well, you want to encode the data of types and terms and substitution in type theory into this. So you have a category of context. So this is category of context and substitution maps. So we've seen in the talk about cubical type theory something like this before. Then you have, so given a context, you want to know what are the set of types in that context. So that gives a presheaf, because depending on the context, you get different types. So that's Ty, so it becomes a presheaf of context. Why is it contravariant? Because substitution is contravariant, right? So that's why it's not covariant. Given a context, you also want to know the set of terms, or termed typed in that context. Sorry, type terms, thank you. So that's Tm at the top. And of course, there's this Tp that goes from Tm to type. And so if you have a typed term, you forget the term and you return the type. And this is given as a natural transformation. Naturality, because we are in the presheaf. These are objects of presheaf category. So this has to be a natural transformation. Naturality essentially says, right, so the typing is stable under substitution. So it gives the operation of substitution. So maybe I draw a diagram here that might help. Okay, maybe I need this. It took a long time before it went out. Maybe I should have continued. Maybe I should have continued instead of using the blackboard. So substitution in type theory says, if I have two contexts, let's call them delta and gamma, and if I have a substitution map, and if I have in the context gamma a typed term, so term A having type A, then I can substitute sigma into A, so I get A sigma, and now that I can also substitute sigma in type A, and this judgment is in context delta. So how do we express this in the natural model? Well, we have this presheaf term, and we have this presheaf type. Gamma is in the category context. These guys are in the presheaf over context. So I take the unit of this, so it lives in the same category now. So this guy is. And this stuff are in the type theory, but you can also imagine they are in category context. This big A is going to be a type, right? So A actually belongs to the set of types in gamma. And by Yoneda lemma, you get A here. Then you have sigma, and by Yoneda embedding, you get a unit of sigma. And then it turns out this substitution can be interpreted as A composed with unit of sigma. This little term A is an arrow from unit of gamma to term, which composes with TP to A. So this diagram commutes. And therefore, so I just expressed all of this above the line. below the line, A of sigma is this composition. Oh, I'm sorry. A of little a sigma is this composition. And by simple diagram chase, we'll see that A sigma composed with TP is capital A sigma, and that explains this rule. So you get that rule. So, okay, there's a correspondence. So that's a typical natural model capturing type theory. Okay, let's hope this works now. Okay, now it's something changed. Now we don't even have blue. Okay.
This came back. Yeah, no, it's good, it's good, it's good.
Oh, okay, good. Let me not touch it anymore.
No, please.
Okay, so I just explained TM, TY, TP, X. So in type theory, we also have context extension or context weakening. So if you have, for example, so if you have a context gamma and a term X in type A, then you can make a new context out of that. So you can add X dot A into the context itself. So this becomes a context.
Should lift it.
Okay. I hope, yeah, okay, extension is still there. Just below that. So this will correspond, so let's now express this into our diagrams in pre-shift category. So let me extend my block a little bit. So if I have unit of gamma that goes to type, and this is A, I want a context, so that's like gamma dot A or something. So this is an operation. And unit of gamma A fits, so this is one of the axioms or part of the data structure here, which sometimes is expressed as saying this TP is representable. That means its pullback along representables is representable. And in this case, this representable actually gives us context extension. So this is the EXT. Right, EXT takes gamma and takes A and gives you a context. So gamma dot A really is EXT of gamma and A. And then we have this map here that we also have to explain. So this is, if you have this guy, you can forget about X and take the return context gamma in. So that's the Y of this plate. Okay.
It's not just your computer falling asleep, I think.
I think so. So it's, I should not panic at this point yet. Okay, wake up. Okay, good. And the last bit of this is saying that this diagram is a pullback diagram.
Oh, and then there's also the bar on the top.
Ooh, there is also this map bar at the top. So let's see what this does. Well, if I have this context, then I can take X, which has type A, and put it here.
You do it by projection?
But this, so both maps are projections. This returns context gamma, and this returns a term. That's why we call it var as variable. Okay. So we call this TP representable typing natural transformation of natural model. And so it's a map in the pre-shift category. In pre-shift category, every map is exponentiable because it's locally Cartesian closed. So you can take its polynomial. As usual, it's sigma, pi, delta, whatever. And then you can actually plug in some pre-shift x and you get this sigma. In particular, you can apply PTP to type itself. So type is a pre-shift. So we can apply it to type, and you get this nice expression. this nice expression is actually a type A with a type family on it. So it's really bundle of types. So why is this bundle of types is important? Because sometimes, for example, you want to form sigma or pi types in type theory. So let's see, for example, pi formation. So if I have like, so in some context gamma, I'm going to forget gamma. Why can I do that? Because I'm in the pre-shift category, so everything is natural with respect to context. So I'm just going to write x. So this is going to be parametric in context, essentially. So if I have this type family in some context gamma, then I can form pi of this. So this is a type family. And then I return a single type. So this is a dependent function type. Sometimes also called dependent product. So it's important that we can form in the natural model an expression like this so that we can apply this pi formation to it. So this data here is just an element of this.
So what, A and B? You want A and?
Yeah, so A is in some type, in some context gamma. Okay, it seems like this is the 10-second rule here. Okay, good. So Steve Audi came up with natural model of type theory, and he proved these nice theorems, which is the natural model models the rules of dependent type theory. Sigma and type plus the universes. So let's just, so that we have everything on the board, let me also sketch something here. So I'm going to push the board and hide the slides. So let's again start with this map, our typing map. Then I can apply that polynomial functor that was in the slide. So that was like PTP at x was A into type and something from A to x. So this bracket A is just notation for the operation of context extension, but I'm going to just use notation like that. So it's really type families in X, and we observed that PTP of type was just pairs of A and type families. So I can apply my polynomial PTP to this morphism because it's a functor, so I can apply to a morphism. Then it turns out, okay, so this is PTP of TP. The pi formation rule up there is just a natural transformation. And naturality means it's stable under substitution. This corresponds to lambda introduction. And the pullback here, you can say, you can encode elimination and computation rule of pi type as this diagram being a pullback. So this is a very slick, very nice modeling of pi types by a single diagram.
See, okay, you're not doing the pi formation rule.
Yeah. So this is pi so pi formation rule is the data of this arrow. So here you have a pair A to B, and this is pi AB. And here you have A and AB depending on some x in A or something. Sorry, B. And this is lambda AB.
Yeah, okay.
Good. Same rule for sigma, and a little bit more complicated maybe for universes. Actually, I think universes we did it with a cube diagram in HIM. So what about intentional identity types of homotopy type theory? So also Garner, 2014, 13, 14, I didn't put the year because I was not completely sure. He gave a talk in CT, I think 2013, where he also said with this magic of polynomial functors and natural models, you can express intentional identity types. I don't have that much time, maybe 9 minutes more. And I also want to reserve some time for questions. So I'm going to, if you want, we can talk about this later, how it works. Anyway, now we have these things in our formalization of all of this type theory captured by natural models and the J rule of Martinov identity types in Lean. So this is this is the structure of pi types. This is the pi former, lambda former, and the fact that that diagram that I drew is a pullback. A similar thing exists for sigma. Here's intentional identity types. I'm going to skip because I didn't even explain what the diagram is, so it's probably not making much sense. I guess like the main thing is like this guy gives you the induction for identity, the so-called J lifting. So that's this natural model ID.J section. So groupoid model. So we have the natural model and we want to interpret it into a groupoid model. This is not what Hoffman and Streicher did. They just gave a direct one. So why did we go through the pain of actually doing natural model? It's because it's one level higher in abstraction. So you can do groupoid model, but maybe you want to interpret natural models into whatever, 2 groupoids, 3 groupoids, infinity groupoids. So we did it at that level of generality. But let's, because groupoid model is done, and it's easier to grasp, so maybe we should see how natural model can be interpreted there, right? So types are going to be groupoids. Terms are objects of these groupoids. Ident, so if I have x and y in same type A, IDA xy is just the Hom type of groupoid from x to y, but because it has to be a type, we see this as a discrete groupoid. So it has to be a group. So clearly here you have, if I have 2 different proofs of that x and y are equal, then those 2 proofs are going to be equal. So that's why it's truncated and doesn't model fully homotopy types. Dependent types or family of types are going to be fibrations of groupoids. So in literature they're called isofibrations. I mean, every fibration here is isofibration. Yeah, so propositional truncation, for example, so the -1 truncation is if you start with a groupoid A, it will have the same object as A, but now you will introduce a unique isomorphism between any 2 elements of A. So basically, you make the type contractible. So if the type you started with was empty, you get empty, so classically speaking. And if it has any elements whatsoever, you will get 1 element groupoid up to equivalence. So either, it's the usual proposition. And the universe, so that in these type theories, there's also an internal universe which classifies sort of like small types or small structure types. So there's a universe of discrete groupoids in here, inside groupoids. And this universe is univalent. So this is something that we are in the middle of proving it in our model. And Ulrich Bocholt, he has shown you can actually do some nice synthetic group theory inside this. So you can, for example, define groups to be pointed connected groupoids. And you can do like lots of group theory with it. you can do some interesting homotopy theory as well. Like you can define things as deloopings, like BZ and classifying spaces. I mean, because you're in one groupoids, you have limited things you can do, but nonetheless, there are some interesting things you can do. You can obtain the circle, for example, homotopically. So as I said, like we are not there yet to have a full groupoid model, but we are getting there. And here are the references. The natural model paper, which is Steve's paper from 2017, the original groupoid model of type theory, which started the whole business of homotopy type theory, is from 1996 by Kaufman and Streicher. And then later, Vladimir came along and observed there's a simplicial model of this, where groupoids are modeled as Kohn complexes or infinity groupoids. And later on, like there's a lot more research. The rest is history, I guess. And then, these are the two formalization projects where groupoid model depends on polynomial functors. I think I stop here.